Neha Pawar is a founding engineer of StarTree and a member of the Apache Pinot Project Management Committee. She's also a friend of mine, and I'm happy to have her on the podcast today to talk about why Pinot is so special. She gives us a little bit of an overview of the architecture and where inside Pinot it's engineered for performance, for its real-time, requirements. And we also kind of take a journey through indexing and pluggability, talk about a feature of StarTree Cloud. This is part 1 of 2. It's a big enough question that we spilled into 2 episodes. But check it out. Fascinating conversation. Listen in to Neha on why Pinot is so special. Hello and welcome to another episode of the Real-Time Analytics Podcast. I am very happy to welcome to the studio today Neha Pawar. Neha is a founding engineer at StarTree, a coworker of mine. She and I have appeared in some Lightboard videos together. She's a great friend. Neha, welcome to the show.
Hey, Tim. I'm so happy to be here.
Good to have you on, and as a I hope a recurring guest. Big question for you, Neha. What makes Pinot special?
Okay, that is a big question, and I could maybe go on for several episodes with that one.
But you're a member of the Pinot PMC and a core contributor. I figured you would be a person who might know. So
yeah, absolutely. So let's start with kind of what makes Pinot special in the broader analytics landscape. Now, all the listeners of your podcast, I'm pretty sure by now have heard that Pinot is a real-time analytics database. Now, analytics and systems and DBs that did analytics existed for a while now. It's not new, but they used to be mostly batch systems or systems that did offline processing, such as data warehouses, and they mainly focused on internal analytics like ad hoc analysis or report-style queries, where latency was not that much of a concern. And the number of users were limited to a few internal users. So the throughput was low and freshness was not that critical.
Yeah, internal in the sense of the consumers are decision makers inside the company, people high up the org chart looking at dashboards or reports or something.
Right. So it was focused mainly on internal decision makers. And then companies like LinkedIn and Uber, they decided that, hey, let's democratize this data. This data belongs to the end users, so why not share these insights and give it back to them? And in the process, also make our product and platforms more engaging and delightful. So this is what we like to call external analytics or end user analytics. So analytics for people like you and me who are on apps and consuming these products and then also getting some analytical experiences in the process. And now this kind of analytics comes with a very different workload and query characteristics. So the scale is usually all end users. So it's going to be really high throughput. And people like you and me, we want interactive experiences. So we want really low latency. And you're going to care about the freshest data insights. So you want to have real-time data ingestion. So all this put together, strict freshness SLA, low latency, high throughput. This workload characteristics is what makes user-facing analytics so challenging. And what makes Pinot special is that it was purpose-built for this from the very beginning. So the design choices and the architecture was just thought about and very well suited for this kind of workload. So think milliseconds latencies, thousands of queries per second, seconds freshness SLAs, very high dimensionality, and at the same time being highly available, reliable, fault tolerant. So Pinot chose to focus on this problem, and then Pinot does this really well, and that's what makes it special.
Every once in a while, when I'm talking to somebody, this is usually in a private conversation, not on a stage, but I'll be talking about the non-functional requirements where, the high concurrency, low latency, that Pinot delivers on and has to deliver on to kind of fill the niche it's trying to fill. And sometimes people will be like, okay, I mean, how magic? I mean, everybody else wanted to build slow databases and you guys just decided, no, we can really do it in 10 milliseconds. Everybody else is just lame. And I have to explain, well, they weren't designed to do that. That wasn't an important constraint. And so they were optimizing for other constraints. So at every level, Pinot's engineered to do that, to do the thing that it's trying to do. And so you're kind of hinting at that. Maybe that's something to dig into, the engineering that takes place at the various levels of Pinot to make it be fast.
Yeah, that's a great way to think about it. We can kind of go take like the journey that a Pinot query takes through the system, and then talk about it at every level or every part of the system that it touches and back. So let's kind of like a brief overview of the very basic components of a Pinot architecture is you're going to have the brokers and then the servers. And brokers are the components that receive the queries from your user clients. They scatter them to the servers. Servers do some computation with segments that they have that they host locally. And then they kind of send the results back to the brokers, and then the brokers merge the results and send them back to the clients.
And segments, for the uninitiated, if you're just joining us at this point in the podcast, we don't always talk about Pinot on this podcast, but when we do, segments are little chunks of tables, right? It's like 100 to 500 megabytes of table data of some number of rows in the table ingested and formatted.
Yeah, so you can think of it as just like a shard. That's a more familiar concept. Like a portion of the data. And usually in Pinot particularly, we take that data and then we also pack it with things like the dictionary, if it's dictionary encoded, or some forward indexes. So these are kind of common concepts, or then some more specialized indexes that we'll talk about in just a bit. So then coming back to our brokers and servers and how the query flew through it, at each stage of this, there are optimizations in place to reduce the amount of work done. So at the brokers are trying to find the least amount of servers that they need to scatter to. And this is done by smart segment assignment strategies and kind of just how you lay out the segments on the servers. So you could use information like partitions. So if your data is partitioned, you could cleverly place them such that certain partitions only go to certain servers. So there itself, the brokers know that, oh, if I'm querying for this partition, I don't need to look at these, say, 10 servers. I only need to focus on these two. So there itself, they're reducing.
Ingesting from a Kafka topic, for example, where the Kafka topic is partitioned, I might say, well, partition 0, 1, and 2 are always on these servers. That kind of thing.
Yes, spot on. So Kafka is kind of very naturally, or any partition stream very naturally fits into this paradigm, and we can make use of it to cleverly place the data. We can also do things like replica groups. So if you're going to have 3 replicas in your whole setup, instead of just spreading them randomly across your, say, 30 servers, you could just say, hey, these 10 servers get 1 replica group, these 10 get the second, and these 10 get the third. So anytime you get a query, now you only need to go to 10 instead of trying to go to all 30 to find all your data.
Okay, just smart intelligence about how replicas are assigned. Nice.
Yeah. So these are kind of the broker to server optimization strategies. Then the next level is from server to segments. So on every server, there's going to be a few segments that it's not few, very many segments that it's responsible for. And the server's always trying to find the least number of segments that it needs to scan. And to do this, it uses pruning strategies. Like, again, it could use partitioning information to say, hey, I don't care about these segments. I'm only going to look at these segments. Or it could use min and max values of every column that we store in the metadata. And there itself, you could know that, hey, if my column doesn't, if my value doesn't fit in this min and max, obviously it's not part of it. So I can ignore this segment.
And that's segment data is min and max on numerical columns.
Numerical as well as timestamp and also string columns.
Oh, okay.
Yeah. And then this metadata, we kind of keep it locally when we load the segment. So you can like very quickly prune out segments that you don't care about.
Okay.
And an even more effective way for segment pruning is bloom filters. So you kind of very quickly just say, hey, you definitely don't need to look at these segments. So these are kind of all the strategies on the server to reduce the amount of work done. And then finally, you come to every segment. So now at every segment, we have strategies in place to try and reduce the number of records that you need to scan. So this is done by, and this is what makes Pinot like super special, is its large army of indexing and aggregation optimization strategies.
Okay. So, indexes, in other words. If podcasts had headings, the heading would be indexes. And this is a super interesting topic. So, take it away.
Yeah. Yeah. So we have like some of the very common indexing concepts like inverted index, where you just have for every value, you have a bitmap of, hey, these are the documents in which you'll find this value. Or you have slightly more, still common, but a little more elaborate concept, just as the sorted index, where you have one column that you can pick and then sort it. So then you can kind of keep better metadata about it. And then you can kind of quickly go find your value. So you don't need to, you can simply say this value starts at 0, ends at record number 1000. Next value starts at 1001, ends at 20,000, something like that. It's kind of
Right.
much.
You can only obviously do that with one column. You
Yes.
pick one column. You can sort of,
Yes. But that makes kind of it super efficient for that column, especially if you know sometimes there are data sets where you kind of have affinity to just querying one column.
Right.
But having said that, all these other indexes can be applied on as many columns as you want. So you have, for example, range indexes, which are great for greater than, less than queries that you very typically run on your time columns. And then you have the more advanced ones like JSON index. So if you have like complex, nested, semi-structured data, which is stored in JSON columns, typically, if you don't have something like a JSON index, what you would have to do is just when you query, kind of get the whole JSON during the query time, try to parse that JSON and then read it, extract the field that you're interested in. And this is obviously not a good setup when you say you want to do low latency analytics.
Famously expensive to do. Yeah.
Mm-hmm. And then the other option is during ingestion time, you just try to flatten everything out, pick out all the columns that you need. But then, of course, if tomorrow that JSON payload has something that you had not thought of before, you have to kind of go and re-add your transform functions. So again, this
And
is operationally.
Re-ingest. Yeah.
Mm-hmm.
It seems like if you know there's something, if you have a column that's a complex JSON object, a blob field that happens to be JSON, and there's something in there that's typically going to participate in a predicate, it seems like you'd want to flatten that. Because then it's a column and you can put an inverted index or a range index or whatever is appropriate there, or sorted or something. But the JSON index is kind of for falling back to where, okay, I've got this blob, it's JSON. Sometimes it shows up, but I don't want to bother to flatten. I haven't planned ahead that much.
Yes.
Is that right? Okay.
That is spot on. And that, and also sometimes you might know all the columns, but it might just be very sparse, like not all, like it'll just be really sparse. So you'll find that particular column in very few rows, and then you could have like hundreds of such columns that you want to extract. So it might not be the best thing to, even if you know them upfront, to just create dedicated columns for them.
Because flattening it would be very sparse. With flattening the JSON would be sparse. Okay. Yeah, that would have other implications.
Right.
Okay. That makes
So
sense.
this is where kind of the JSON index, you don't have to do anything. You just have to point, hey, this is my column that is JSON, and Pinot will index each and every field of it as it finds it, and you'll be able to query it super fast. We've seen kind of latency drop from like tens of seconds to just few milliseconds when we
Oh,
have
okay.
kind of benchmarked this.
Okay. So the JSON index is not a second class citizen of the indexing community. It's fast.
It
Okay.
is really fast.
Okay.
And this is going to unlock a whole bunch of use cases like log analytics and uh, text analytics and just.
Yeah. Okay. Where the alternative would be a very large number of sparse columns. We're saying, look, just have your semi-structured data.
Yeah. Yeah. Yeah.
And we'll build a tree. I guess there's some kind of tree structure that's going to get built in the implementation, and we'll take care of you.
Exactly.
Okay.
And then there are more geospatial index. So if you have coordinates, then
explain that in detail.
it's very easy to run location-based queries. Like, for example, in Uber dashboards, you have, hey, find me all the orders within so and so miles from where I am. Very fast to run such kind of queries. And then
How about text? There's two different kinds of text indexes. Talk to us about that.
Yes, so we have Lucene-based text indexes as well as native text indexes. And again, they're used for queries that have, hey, find me something like this string or regexp match, those kind of queries. Again, text analytics, log analytics, very useful indexes for those.
Right. If you just got a blob. And the so-called native text index is just Pinot zone implementation. And if I understand that correctly, it's a subset of the Lucene features, but faster. Is that right?
That's right.
Okay. So if you can get it done with the native index you want to, if you need Lucene, good news, Lucene is there, which, I just feel like every time Lucene is one of those projects, every time it comes up, I feel like we should stand or something. It's 20, 25 years of text indexing, and it's not going to stop anytime soon. So, yeah. Anyway, keep going.
And then we have our favorite index, which is the StarTree index.
Yes.
This is kind of it's a filter as well as an aggregation optimization put together. It's kind of like Pinot's smarter way of doing a materialized view. So here you can pre-aggregate dimension combinations like you would in a materialized view. But in StarTree index, you can do it for only certain dimension combinations. You choose the aggregations, you choose the dimensions, and most importantly, you choose how far you want to go in kind of computing and materializing those combinations. So you could configure something like, hey, I am okay with doing scanning of 10,000 rows. That is the amount of overhead that I'm willing to take. So if you start seeing that any combination has only 10,000 rows left, stop doing further combinations. Versus in like a traditional materialized view, you don't have that choice. You just have to, once you decide, hey, these are my dimensions, you pretty much pre-aggregate for everything. And of course, that's really bad on the storage footprint.
Yeah, there's space-time trade-offs there.
Yeah, versus StarTree lets you kind of choose the overhead between pre-aggregating everything or doing everything on the fly.
Got it. We're planning an episode in the near future that's a deep dive on the StarTree index. So, stay tuned for that. It's actually pretty cool. It is one of those things where when people first see it, they think something is broken, like, oh, this result must be cached or something, because it's just too fast. But it's a neat idea, and there's a bread and butter filter and aggregate. If you're computing an aggregation of some metric column, and there are a few predicates that might show up in your where clause, like 2 or 3 columns that are often there, that's a super common query type in an OLAP database, and it's designed to optimize for that. So it's cool.
And these were kind of all the indexes that we have in Apache Pinot. There's another one that I'd like to call out. It's the sparse index. This one, though, is only available in StarTree Cloud. It was added as a plugin, and that's actually a very good topic for us to talk about next, the plugin architecture for Pinot. But before that, so sparse index, it's kind of like this middle ground between a Bloom filter and an inverted index. So where Bloom filters will just tell you, hey, go query this segment or not. It's at the segment level. And inverted index will tell you the exact document IDs that you need to go look at. Sparse index is going to tell you, hey, go look at these chunks of this column. And that's where you will find your data. And you might wonder, hey, why not just create an inverted index in such cases? A, because sparse indexes are much lower in storage footprint.
Okay.
And B, sometimes if you have like a super high cardinality column, and if so in that case, building an inverted index can kind of get out of hand.
Yeah, it doesn't work as well. So inverted indexes assume relatively low cardinality.
Yeah. Plus, if you have like a highly selective column, so typically like a high cardinality column, which is like a transaction ID or a UUID.
Well, that would be very high cardinality.
They, at the same time, tend to be very highly selective.
Right.
So it kind of fits perfectly. You don't need to build like a whole elaborate inverted index where you pretty much might just end up saying, hey, here's my number of, all the values are equal to the number of total documents, which is kind of very wasteful. You are just kind of saying, hey, you'll find these values in these chunks. And you might pretty much sometimes match to just like 1 or 2 chunk in your whole data buffer. Okay. So that'll kind of work out really well.
Okay. Because those are characteristics of columns that kind of suggest a good old transactional like B-tree index. Which is not, I mean, none of these is that, but this is sort of like the Pinot or the OLAP approximation of that. Because high selectivity queries, if you have a workload that's locked at lots of high selectivity queries, you don't have an OLAP workload. But sometimes in one's OLAP workload, these things kind of creep in. And so this is our answer to getting part of the way there.
Yeah. Yeah. And also, like the Pinot sparse index is very kind of special compared to some of the approaches other systems have taken, because you don't have constraints like you have to build it on sorted column, and you don't have constraints like, hey, you can only do this on one column. You can pretty much, like our other indexes, build this on as many columns as you want.
Nice. Okay. And again, to be clear, that's a StarTree cloud feature. That's not an open source Apache Pinot feature, the sparse index.
Yes.
Cool. Okay. Good to know. There are other things in, the broader story of Pinot. Anytime we talk about those, we'll call them out carefully that like, no, this is a commercial thing, feature of the cloud, that StarTree offers, or, otherwise by default, you can assume we're talking about open source Apache Pinot. There are those two things in the world. Now, I'm looking at time, and I'm imagining. I just started asking you what makes Pinot special, and you said at the beginning this might take more than one episode. I think it's gonna. I kind of have an idea what else you might be talking about, so I wonder if we should reserve the rest of the list for next week's episode. What do you think?
Yeah, that sounds great to me. Always happy to hang out even more with you.
All right. My guest today has been Neha Pawar. Neha, thanks for being a part of the Real-Time Analytics podcast.
Yeah, my pleasure. Thanks, Tim.
And there you have it. If you feel compelled to help us spread the word and grow the Real-Time Analytics community, you can give us a rating on Spotify or Apple Podcasts or wherever fine podcasts are sold. If you're watching us on YouTube, hey, subscribe and, of course, hit that notification bell. And you can always share your favorite episodes on LinkedIn or Twitter or wherever it is you do social media. Thanks, and I look forward to talking to you in the next episode.